Okay, in our last videos, we looked at the idea of a solution and then the theory behind their formation. Today, we get to do something fun. We get to look at the math. So we're going to start out by first describing concentration, and then we'll get into the math behind concentration. But concentration is pretty straightforward. It's the amount of a solute in a solution. Specifically the amount dissolved. We're going to assume that it's going to be a homogeneous solution. All right, and most of you are pretty familiar with concentration, so if you've ever made Kool-Aid or some sort of juice, you can adjust the concentration by adding more or less water, right? Thereby changing the amount of solute dissolved in a given amount of water. Okay, so let's take a look at the two different ways we tend to do this. So method number one tends to be the most common with chemists, and this is molarity. And molarity is pretty common, at least within my field, which is organic chemistry. And molarity has the symbol capital M. That's why capitalization matters a lot. So capital M is usually molarity. Lowercase m is often mass, so we want to make sure we don't confuse people. But molarity can be calculated by taking the moles of your solute divided by the liters you have of your solution. So it's a pretty basic measurement. People like it because it's based on the mole system. So let's do an example here. So let's do an example where we have 100 milliliters of solution. And I'm going to make this exactly 100 milliliters, so I'll put a decimal there. Oftentimes we use volumetric flasks when doing these measurements. We're going to assume things are precise. And we've got 100 milliliters of solution with 2.60 grams of NaCl, which is our solute. So really we're just making some salt water here. Well, first things first, we would need to find the moles of sodium chloride. So let's do that. So let's go ahead and do the math here. So moles of sodium chloride. Well, we know we have 2.60 grams of sodium chloride. To convert from grams to moles, we need to know the molar mass. So in this case, we know that 1 mole of NaCl, let me zoom out a little bit, is going to be equal to 58.44 grams. And we know this because we can go to the periodic table, add up the mass of a sodium atom plus a chlorine atom to get that formula weight. So we want to cancel out our grams unit. I'll put that on the bottom. And we know that grams right here is paired with 58.44. So I'll put 58.44 on the bottom, which means we must have 1 mole on the top. Okay, so we've canceled out grams of sodium chloride. That looks good. That leaves us with moles of sodium chloride left over. And in this case, I'm getting 0.0445 moles of sodium chloride. And again, we want to keep track of sig figs here. So I'm sticking with 3 sig figs in my final answer. All right, now let's do liters of solution. Okay, whoops, that's not correct. There we go. So we started out with 100 milliliters, and this is just my decimal to indicate that this is an exact measurement. Okay, and we know that that 1 milliliter is going to be equal to 10 to the negative 3 liters. And the reason that we know this is milli stands for 10 to the negative 3. So we can use this as another unit conversion. Okay, so let's cancel out milliliters. I'll put that on the bottom. And we want to go to liters, so I'll put liters on the top. And if we look at it, we could say, well, 10 to the negative 3 is paired with the liters unit, which means I need to put 10 to the negative 3 with the liters unit here, and then 1 with the milliliters unit down here. So now we can cancel out milliliters, and we're left with liters. So now if we plug this in, I'm getting 0.100, and our units would be liters. Okay, so now we can say that the moles of solute over liters of solution would be equal to 0.0445 divided by 0.100 liters, which would give me a value of 0.445 molar. And it's important to remember that molar is the same thing as moles over liter. You can use them interchangeably here. Okay, so hopefully this makes sense. Let's do another example though. So in the second example, we're going to do things a little bit differently. So I'll just write example 2 down here. And I'll say, how would we prep 1.00 liters of a 1.50, let's keep 3 sig figs in each of these, molar cobalt to chloride solution. So this is a bit more abstract, right? So let's try to kind of work our way through this. Well, we know that we need moles of solute over liters of solution. This equals our molarity. Okay, we don't know the moles of the solute that we need, right? That's not given in this setup. So we'd say moles of solute is what we want to solve for. In fact, let's just change this to the x variable. And then liters of solution was already given to us. We know it's going to be 1.00 liters of solution. And we know that the molarity is going to be 1.50 molar. Okay, and if you wanted to, you could even say, well, we know that molarity is the same thing as moles over liter. So if you wanted to break it down into a math problem like this, that's perfectly acceptable. So now let's solve for x. Okay, so we could say x would be equal to 1.50 moles over liters times 1.00 liters. It doesn't really matter if you express it this way or like this, it's completely equivalent. Okay, and then by doing this, we could cancel out our liters unit and be left with our mole unit. And let's go ahead and figure out how many moles we need. And if we just do this quickly in our head, 1.50 times 1 is going to be 1.50 moles of COCl2. Okay, and that leads us to our next step. If we have 1.50 moles of COCl2, and we need to figure out grams because we can't measure things out in moles in the lab, we need to get rid of this moles unit. And we need to get our grams unit. All right, so now the question is, how do we do this? Well, we know that 1 mole of COCl2 would be the mass of 1 cobalt atom plus 2 chlorine atoms, which in this case is going to be 129.9 grams. All right, so when we go to plug this in, we could say, well, 129.9 should be with the grams unit, and 1 should be with the mole unit. We can cancel out our moles, and we could be left with our units in grams. There we go. So let's type this in. So I've got 1.50 times 129.9, and I'm getting a value of 194.85 in my calculator, but I can only have 3 sig figs. So I would say we need to round up to 195 grams of cobalt to chloride. All right, so great. This is how much we need to form 1 liter of solution. So let's show you how you would do this in a lab. And here's what we typically do in a lab setting, right? So what you have are these things called volumetric flasks. And it's really hard to see here, but there's a line right there. And this is an exact measurement. So very precise. These are highly calibrated to make sure that it's an exact volume when you fill up liquid to that mark. So what we would do first, I would just ignore all of this down here, is we would add our 195 grams of cobalt-2 chloride, and then we would fill to the line with water. So fill to line with water. And then you can put your cap on. They don't really show it here. Invert it, make sure everything's mixed, and you would be left with your solution at the correct molarity. This is how scientists would prepare standard solutions in labs. All right, I hope that makes sense. There's a ton of practice problems with these. Obviously, you can do a lot of algebra with this basic equation right here. So if you're given molarity in liters, you can solve for mole. If you're given moles in molarity, you can solve for liters, things like that, just using simple basic algebra. All right, so like I said, molarity is really common in chemistry, but there's another one that also comes up a fair amount. This is just percentage. And percentage calculations, again, they show up pretty commonly in industry, but a percentage is going to be equal to a part divided by a whole times 100, right? This is something we saw pretty early on in this course. Well, let's see the various ways we can use this for concentration. The first one is percentage weight. So it's WW. So this is equal to your solute mass divided by your solution mass times 100. And I'm going to make a little note here that these must be the same units. Right? So if your solute was measured in grams, your solution should also be measured in grams. You don't want to have grams on top and kilograms on the bottom. That would mess things up. So it needs to be the same. All right. So this one's not very common. And the reason for this is normally solutions aren't made using solid-solid mixtures with the exception of alloys. So you might see this maybe with gold. So you might see a percentage gold in an alloy, but it's not common for liquid solutions. So only common for solid, whoops, not sold, solid solutions. All right, so that's one common one. Let's do the next one. The next one we're going to look at is weight to volume. So it's WV. This one's a lot more common in chemistry. So this time we still do solute mass. And it's always going to be in milligrams. And the volume is going to be on the bottom. So this is solution volume. And this is going to be in milliliters times 100. And so this one tends to be common for solids dissolved in liquids. It's similar to molarity. However, we're not dealing with moles over liters, we're dealing with mass. And so this practically is easier to use quickly in a lab setting, but it doesn't let you know how many moles you have. You have to do another calculation. All right, and then our last one, you can probably guess, is going to be volume. And this is going to be our solute volume divided by our solution volume. And just like before, we have to use the same units. So if we're measuring in milliliters for our solute, we need to do the same for our solution. And we're going to multiply this by 100. So this is common for a liquid-liquid mixture or a gas-gas mixture. So this is most commonly used for liquids, but occasionally you see it used for gases as well. So like I said, it really depends on the situation and the states of your solute and solvent, which one of these you might be more likely to use. Okay, so let's do an example calculation. So 90 proof vodka, and I'll just make this exactly 90 proof, just to keep things simple, is 45% volume by volume ethanol. All right, the rest is just water. So how much ethanol is in 44 milliliters? And 44 milliliters, I actually looked this up. That's about the average size of an American shot, give or take. All right, so we know that percentage is going to be equal to a part over a whole times 100, right? All right, so let's kind of write this out a little bit differently. This is just our standard percentage. We know that we're trying to solve for the part here, so I'm going to label that as X. The whole was 44 milliliters, and we're going to multiply this by 100, and this is going to be equal to our 45%. So if we want to do this really quick, we could say that let's just divide each side by 100 to get rid of that 100 unit. So X over 44 milliliters is going to be equal to 0.45, and X is going to be equal to 0.45 times 0.44 milliliters. And let's go ahead and do this math really quick, which would come out to, let's see, 19.8 milliliters, but we can only have 2 sig figs here. So we would want to curve this up to 20 milliliters exactly. So the decimal indicates that this is exact here. So it's pretty easy to prep solutions like this. All right, let's do another one. Kind of like we did before, let's now imagine that we're trying to prep a solution. So I'll just call this example 2. All right, in example 2, we'll say, how would you prep a 250 milliliter solution of 0.900% weight to volume sodium chloride? All right, so again, we need to kind of set this up, and we'd say, well, we know we need to do weight to volume, so it's going to be the mass in grams, right? So it's going to be mass in grams of our solute, but divided by the volume of solution in milliliters times 100. All right, so let's go ahead and write this out just as a plan. And we'll say this will be our weight volume percent. But now let's go through and plug in our numbers. So we're not given the mass of sodium chloride that we need. We need to solve for that. So I'm going to label that as our X variable. Our volume of solution was given as 250 milliliters. And luckily, it was given to us in the correct units. So we're set to go here. And then we need to multiply by 100. And this would be equal to 0.900%. All right, so now let's do some math here. We could say that X is going to be equal to 0.900 divided by 100. That would be my first step. But then we would also want to multiply by 250 milliliters. And if you go ahead and do this, you'd say, well, we need 2.25 grams of sodium chloride. And just like I showed you that volumetric flask picture above, we would add this to our volumetric flask and then dilute up our sample volume until we hit 250 milliliters in a graduated cylinder, or sorry, not graduated cylinder, volumetric flask, kind of like we saw up here. All right, so last one. I'm sorry this video is a little long, but I just want to make sure we hit this key point. And this is solution dilution. And this is really useful if you're given a solution of one concentration that you need to change to another. And it's pretty easy. It's M1V1 equals M2V2. So this is the molarity. Or actually, let's just make this concentration. Of solution 1. This would be the volume of solution 1. And this would be the molarity is usually what's used here. Let's just stick with this as molarity. I want to avoid confusion. Sorry if I messed up your notes. Of solution 2. And then volume of solution 2. All right, so really it says if we're given the molarity and volume of 1, we know how many moles we have in this solution, right? And then same thing over here. So we can use this to do some planning. So I'll show you an example of this. And let's say we need to prep 1.00 liters of 0.125 molar solution, or sorry, sodium or nitric acid solution from a stock bottle of nitric acid that is 15.9 molar. Okay, so let's think about this. Let's just call these values M1 and V1. All right, so we know that M1 V1 equals M2 V2, and down here, the only thing that we're really given is M2. Okay, however, we need to figure out how much of the stock bottle volume we need. So determine V2, which is the amount needed for dilution. Okay, so let's do this really quick. We could say, well, M1 was 0.125 molar. V1 was 1.00 liters. That's the amount we're going to dilute up to. And then M2 is going to be 15.9 molar. And then we need to solve for V2. Okay, so if we do this, we can say, well, V2 in this case must be equal to 0.125 molar times 1 liter divided by 15.9 molar, which gives us a value of 0.00786 liters, which is the exact same thing, especially if we use sig figs, we can only have 3 of, as saying 7.86 milliliters. So what we would do is we would take 7.86 milliliters from the stock bottle and dilute to 1.00 liters to get a 0.125 molar solution So this is a handy trick, especially if you're in a lab setting. The main thing to remember is you want to make sure that your units cancel out correctly. So in this case, molarity and molarity cancel out correctly, and we're left with liters behind. And then in the last step, I did a separate conversion. All right, I hope that helps, but let me know if you have any questions.